there's 5 values. There's 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if you were to look at a unit circle, you would see that this is 0, 1, 0, minus 1, 0. So when you graph this, that's a terrible graph. When you graph this, you're starting at 0, 0, and then the first one is pi over 2, and then pi, and then 3 pi over 2, and then 2 pi, but you're graphing these points 0, 0, pi over 2, 1, pi 0, 3 pi over 2 minus 1, and then 2 pi comma 0. So what you might do is want to connect them like that, but if you were to graph this on a nice calculator, you would see that it's got a nice smooth form like that. So the graph you have on your piece of paper isn't quite right. It doesn't actually go back down below the x-axis.
Yeah.
And this, when they say the 5 key points, it's these 5 right here.
Okay.
So it sounds like, well, no, sorry, it looks like you need to know this before your diagnostic, which it means you got to know the parent function. So now we're going to do the same thing for cosine. Oh, and by the way, if you go to Desmos, or if you have a calculator on this, you can just graph sine. Make sure your mode, though, is in radian when you do that.
Okay.
And you should get a graph like this. Now for cosine, it's very similar, but not to be confused with sine, which I know doesn't help you, but it's the same. It's the same 5 x values, but the y values are slightly different. It's 1, 0, minus 1, 0, 1. And the graph of this starts high, starts at 0, 1. This is pi over 2. This is pi, 3 pi over 2, and 2 pi. So 0, minus 1, 0, 1. So it has this curvature because it actually oscillates forever. So you have to kind of show these bends. The first time you do it, unless you're a real artist, you probably won't get it, but the more you do it, it'll look smoother. Actually, your lines, there's nice curves on your graphs that I see on the paper there. And that's for cosine, sorry, cosine x. Sometimes it's good to kind of look at them side by side, sine versus cosine, just to see which ones are there. I would rather not do tangent unless you feel really strongly that we should, just because it's much more confusing.
Can we just talk about it just briefly to get like a general idea?
Yeah, I'll give you the condensed version. I'll give you the 3 coordinates that you care about with tangent. So you care about minus pi over 4, 0, and pi over 4. So pi over 4, it's 1, and then 0. This doesn't actually give you a good sense of what the graph looks like, but the shape is that it has this. This is pi over 4, minus pi over 4, and this is pi over 4. It has this sort of snaking pattern, like this, and then like this. There are these vertical asymptotes, which I don't want to get into, but it's very different. It does not oscillate forever. It actually, well, there is a pattern, but it's bounded between these two. So you got to remember that it looks like this.
Okay.
It's tough to get 5 points on this one. It just doesn't, they're just not nice.
Okay.
All right, so let's look at this transformation. Then I was thinking we could do a couple of transformations like this. Towards the end of last year, you were doing a bunch of these. So your lessons are always available on my YouTube channel. So if you ever need to go back and look at one, and if you use keywords, you probably can find one for transformations pretty fast. So this one has a bunch of transformations. It's got this x minus pi, that's a transformation. It's got this 1/2, that's a transformation. It's got this 3, and then it's got this +1, that's another transformation. Let me get this frame better. Okay. Okay, so notice this pi is inside parentheses. It's analogous to like x minus 2 squared. We would say that that's, or let's do a 3 there. We would say that that's 3 right. 3 right because it's minus. So you would say here this is pi right. Or right pi. Pi right, right pi. If it were plus pi, it would be pi left.
Mm-hmm.
Okay, so any questions on that?
Not so far.
Okay. The +1 is last, but I'm going to do it first here or second here. The +1 is a vertical shift, so it's 1 up. Okay, but the order matters here, and that's why it's down here at the end. I'll explain that later if we need to, but those are the ones that I think are probably the most clear. Now this 1/2, it's inside parentheses. When stuff is inside the parentheses here, those are horizontal. So the 1/2 is a horizontal. Now, because it's, and this is where it's awkward, because it's less than 1, it's actually a stretch. The rules are kind of reversed when they're inside parentheses.
Okay.
Now, more awkwardness, depending on your instructor, you can either say horizontal stretch of 1/2, or you have to use the correct language. Let me see if your instructor did that, or or if that was written down. So I don't see like much written here, but it's actually the reciprocal of this is how much you're stretching. So it's like that's one option. The other option is you could say factor of 1 over 1/2, which is 2.
Mm-hmm.
But if it was a compression, which occurs if this number is greater than 1, like let's say the 3 was in here, it would be a horizontal compression of 3 or by a factor of 3. So I'm sorry, I know that isn't super clear. I'd probably just stick with this to like avoid anything weird happen on the exam. So the main thing is that it's a stretch if it's less than 1, it's a compression if it's greater than 1. The number 3 here is this 3 on the outside, so that's a vertical stretch of 3. It's just that number. Okay, so let's do another one like this one. We'll just slight variations on the numbers to get you to write down the correct kind of wording here. So let's go 2f of 1/4 x minus pi over 2 plus 3. So again, there are 4 transformations here. I've made only numerical changes from the previous one. Will you give this a try, please? How are you doing on your list?
I'm done, I think.
Okay. So give me your first one.
So my first one was the minus pi over 2. So
Okay.
do I just say like pi over 2 to the right?
Yes, or right
Okay.
pi over 2. Either way
Okay.
is fine. Okay. And where did you go next? Hopefully it was the
Um,
1/4.
yeah, a horizontal stretch, 1/4.
Okay.
A vertical stretch of 3 and then up 3.
So actually of 2. There's a 2
Of
there.
2, yeah.
Yeah, and then up 3. Okay, perfect. All right. Okay. So the only thing that could change based on this is it could be right or left. Okay. They could throw in a negative. So a negative would be right in here. It would be a 3.5. It would be a flip over the x-axis. And then they could also actually put in a negative right up here. That would be like a 2.5. That would be a flip over the y-axis. But I don't know if that's going to be the case. There's so much unknown. Are you getting a feel for what the instructor might ask you, like things they're emphasizing, or?
Yeah, a little bit.
Okay. All right. So the next question on this review, it's based on this, but I just want to review some things with you. Sine of x and cosine of x have period 2 pi. And what that means is that they repeat every 2 pi. So the graph of sine looks like this, and then it repeats. It's exactly the same. It goes up, down, down, up. Same with cosine. And that's what that means. Like this period right here, this block is the same as the next block. Just over and over and over and over and over and over and over again. Okay. But there are transformations that affect the period.
Okay.
So for example, it's a little bit odd how they're doing here, but let me I'm trying to debate it. So let's say it was sine of 1/2 x. The period is 2 pi divided by b, and b is this number right there. So it would be 2 pi over 1/2, which is 4 pi. If the cosine of 4x is given, the period is 2 pi over b. B this time is 4. It's the number in front of x. So it's 2 pi over 4 or pi over 2. So that what the period's like, it shrinks or stretches out the repeating part. Okay. Now back to your problem, like what you care about. So let me go grab it. This one right here. Okay. So this one, what the problem is saying is like, what if this is a sine function? Okay. This is your K, this is your B value right there. This is B.
Okay.
So your problem, the problem asks something like, what is the transform period for the sine graph? So the transform period is 2 pi over b, or 2 pi over the 1/2, which is 4 pi. It's that number right there. There's a lot more that's going into this, but I don't see the need to get into more detail than that. Like that's what you want to remember. It's 2 pi over b. B is that number in front. Call it good.
Okay.
The midline is only affected by this number right here. So the midline, what is the if you're asking yourself, well, what is the midline, Matthew? The midline is I think the center line is a better wording, but it's the one that divides the top from the bottom. So it's normally at 0. It's normally y equals 0. But if you shift the graph up or down, this is a shift up or down, that affects the midline. Hang on just a second.
Okay.
All right, I'm back. So the only effect on the midline is this vertical shift.
Mhm.
So that like a no card or something to remember that. There's really nothing else that affects that. And it really, I mean, this thing with tangent, it's just not, tangent's a whole nother ball game.
Okay.
So I'm sorry, are you there? I apologize. I've been muting myself unnecessarily. So I've got a problem I know we have not looked at yet on from the other night. So I mentioned there were some fractional exponent problems that we've not done. So I'd like to start there if that's okay.
Okay.
So these are kind of like square root problems where you want to isolate the variable, x to the 3/2 or x to whatever the power is. So you do that by first adding 7 to both sides, 54, and then dividing by 2. So 3/2 equals 27. And this is where you have to remember the some formulas here. So I don't like this formula. I actually prefer to remember this, that this is the square root of x to the 1. But that helps me to actually write out the formula because it's the nth root of x to the m. And so what, why am I doing that? Because you do actually want to rewrite this one. You don't just want to raise it to the 2/3 power. That'll be problematic later on. So 2 means it's the square root. It's the square root of x cubed. And hey, Julia, so where we left off is that I was telling you that you don't want to just apply an exponent to both sides. You actually want to rewrite it. There's a couple of problems where that actually matters. It does not in this one, but always exceptions in math. So how do you undo a square root? Well, you undo a square root by squaring both sides, right? Do you know if you would have a calculator for a problem like this? Because if you don't, we'll just do it a slightly different way.
I think we might. I'm not sure.
Okay, so I'm going to assume you don't for the moment. 27 is really 3 to the power of 3. And so when you have an exponent to an exponent, you can multiply them. So it's really 3 to the power of 6. Okay, and you could figure that out if you needed to. You could also multiply 27 times 27 and get that number. But on the left side, we have x cubed. Now, how do you undo a cube? Well, you use a cube root. A cube root is really 1/3 power, like this. So you undo a cube with a cube root or a 1/3 power. On the right here, you multiply the exponents, so it becomes 3 squared or 9. Okay. Now I'm going to go back to this line right here, and I want you to see that we could have solved it right here, but this is potentially you miss a solution. So you can undo the exponent with the reciprocal of it.
Okay.
And that works because the reciprocal, 3/2 times 2/3 is 6/6, which is 1. And that's what we want. We want x to be by itself. On the right, this is 3 cubed. And by the way, there's always SAT prep questions that have to do with exponents like this. So there's value in manipulating these. So you multiply the exponents. 3 times 2/3 is 3's cancel, so just 2 or 2/1. So it's 3 squared, or it's still 9. Okay, but my point was, you got to be careful that you don't miss one, which happens from time to time. I'm looking at your exam to see if there's any more. Yeah, let's do one more here of this type. Kind of the same. It's slightly different, but okay. So here's a problem. It's kind of like the ones we just did. So you might say, hey Matthew, can't we just undo with the 3/2 to both sides? And the answer is yes, but you might miss a solution. So let's use that. X to the 1/2 means it's the square root of x to the 1, or 2 to the 1, which means that whatever's on top goes outside. It's the x root of x to the m. So that means that it's the cube root of x plus 2 squared equals 9. Okay. How do you undo a cube root? Well, you cube it. You cube both sides. Okay. So that's 9 times 9 times 9. It ends up being 729. Okay. Now, this is why you have to be careful here. When you take a square root of both sides, actually, let me do that in another line. That way you can see it later on. If you take a square root of both sides, it's plus or minus. And that's key. That's really key here, because you can miss one of the solutions. So that's the risk with if you just blindly said, oh, well, it's just 3/2. So the answer is whatever it is. You miss one of the solutions, which is really bad, really bad. I'm sorry. Did I not? Oh no. Okay. All right. So now on the left here, we undo it. It becomes x plus 2. On the right, this is 9 times 81 and 9 times 9. So you end up getting a 9 that comes out. So this is plus or minus 9 square root of 9. And what? This isn't right. Sorry, I'm losing my mind here. Wow. Okay. Sorry. So this is correct, but it's also 27 squared. I was just shocked that this was working. So this becomes plus or minus 27. X plus 2 equals that. So it's really two equations. It's 27, x plus 2 equals minus 27. So you subtract 2 from both sides, and you get x equals 25, x equals minus 29. So in summary, for these types of problems, the rule is, if the bottom exponent is odd, you have to do what we did. If the bottom exponent is even, you can just undo it. I think that's hard to remember, but that's up to you if you want to do that, or if you just want to I mean, who knows? Like, we don't even know if we're going to get one of these. Like, there's so many. There's literally there's tons of problems here. So I wish I could be more helpful, but okay. So we're going to go to operations with functions.
Okay.
This is like combining functions through adding, subtracting, multiplying, dividing, and maybe some composition. Okay. But
Okay.
here's part A. It says g minus f of x. And what that means is you take g of x, and you subtract f of x. So g of x is this thing on the right. That's the x squared plus 5. And then f of x is this 2x cubed plus 7x squared minus 2x plus 4, like that.
Mhm.
Okay, and there's a reason I put this in parentheses, because you're going to distribute this negative to everything. That's also an SAT prep thing. There's a problem, always a problem where you have to distribute negatives, and you have to know to distribute them to everything. And then you have to combine like terms. Okay. There's also kind of a preference to put things in what's called descending order. So this minus 2x cubed would come first, but then the x squared combines with minus 7x squared, so minus 6x squared plus 2x, and then 5 minus 4 is plus 1. All right, so the next problem is f over g, f over g. So the divisions are actually a lot nicer, because you actually just generally have to write whatever f is. So f, the top one over the bottom one here, and you're done. So generally dividing, you just write them. Sometimes they ask you questions about the domain, but it does not appear to be the case in this one.
Okay.
So let me just talk about this problem without doing it, because this one will take a bit of time. So this problem, at first glance, you might think like, oh, maybe there's some sort of grouping or technique that works but you can't factor out enough to sort of get this to work. So this is a calculator problem.
Okay.
And or it's synthetic division. And have you been doing synthetic division in class?
No.
Okay. So we will skip that. All right, so the next problem here that I'm seeing is it's graphing a logarithm. And that would be another thing I would sort of want to know is, do you know if you've been doing logarithms in your review? Is that something we should do?
Yeah, it's mostly been a lot of like graph and transformation work in class.
Okay, sounds good. So you have to know a few things about logarithms to start. So I'll go log base 3 of x. The graph of this looks like the following. It starts down at minus infinity and does something like that. And this point right here is 1, 0. Okay.
Mhm.
So the property of logarithms that you have to know is that the log base b of 1 is always 0. So it doesn't matter what the base is. When there's a 1 here, it's always 0. And you don't need to know why that
Okay.
is, but like you need to like be able to recreate that. Okay, so the first thing we're going to do is parent functions, transformations of parent functions. So there's two. There's this 3, this 3 out in front, and then there's this -6. Okay, and the 3 is just like what we've seen before. When it's out in front, it's a vertical stretch.
Okay.
Vertical stretch of 3. -6 means down 6. And for our purposes, what's interesting is both of these affect the y. They are changes in y only.
Okay.
So the reason that matters is if you knew the parent function, if you knew the graph of x, and then y equals log base 3 of x, if you knew the parent function, you could use these to just manipulate the table. Okay, so I already mentioned one point. I mentioned that when x is 1, y is 0. Because it's base 3, that's the next value we're going to choose. We're going to put 3 there. So this is log base 3 of 3. This 3 is that one right there. And whenever these numbers are the same, it's the output is 1. And again, we're doing the parent function now. We're not doing yours. We'll come back to yours. So the next one is 9. Log base 3 of 9. And this is where you need to know a few properties of logarithms, which is covered in pre-calculus. So I'm surprised you're seeing it here, but this is log base 3 of 3 squared. The 2 actually comes out in front. So this becomes 2 times log base 3 of 3. Log base 3 of 3, whenever your base is the same as that, when those are the same, that's 1. So 2 times 1 is 2. And that might be enough here. I think it says you only need 3 points, at least 3. So 3 works. Okay. So the reason this is helpful is for your graph here. I mentioned this before. These transformations only affect the y, so you can actually use the same 3 x values.
Mm-hmm.
But these affect the y, and you have to know how they affect the y. So a vertical stretch of 3, you're literally multiplying by 3. You're multiplying these y values by 3. But then down 6 means you're subtracting 6 from each of them. So you have to do 2 things. You have to first multiply by 3, and then second subtract 6. Now, if that's confusing, I mean, unfortunately that's the nature of these. Like, that's how you use the parent function. We could also put these back into the equation, but you end up doing the same thing. You end up multiplying by 3, subtracting 6. So in case of 0, when you multiply by 3, that's 0, and then you subtract 6, it becomes -6. And then this one, you multiply by 3 is 3, subtract 6, so that's -3. Multiply this by 3, that's 6, and then that's subtract 6 is 0. So these are ordered pairs. These are 1 minus 6, 3 minus 3, 9, 0. So your graph ends up looking like that. But there's so much more that goes into logs. That's why it's like, I wouldn't, if this is unclear, if all the stuff on the right is unclear, try to just focus on the transformation stuff for that. Okay. So in terms of other stuff here, this is where it crosses the x-axis. That's your x-intercept. This one does not have a y-intercept. It actually has a vertical asymptote at y equals 0. So now the end behavior. So the end behavior is like as x goes to infinity. So that means to the right. So as you go to the right, okay, what happens to the graph? Does it go up or down? Like, and this is where you got to know the logarithms actually go up forever, even though it takes them a while to go up forever. So in this case, y goes to infinity. Now, normally it's x goes to negative infinity, but the problem is we actually don't cross. So this time it says x goes to 0. So that's another little wrinkle with logarithms. And these are all their own units. Like you would spend a full chapter on graphing logarithms, figuring those out. But you can tell me for sure what y does. How far does y go down? Well, it goes down forever. It goes to negative 50 or negative infinity.
Okay.
Okay. Let's do another one of these, I guess. I think this would be helpful to do. Again, you'd spend like a whole unit on transformations. Catalina Foothills is notorious for, they give you like the same, you get a practice and then you get like the same 4 problems on your exam.
Yeah.
So that's the good thing. I was seeing something on social media today about people, they're very excited about the formative, the summative, and I don't know what the third one is, but I think it's very confusing for a student. You're like, does this count or not?
Yeah, it is.
Yeah, it's like, well,
Yeah.
treat it like it counts. That doesn't work that way. I mean, competitions are competitions for every
They're like, use it for study material. Yeah.
All right, so there are 3 transformations in this problem. The first one is this x plus 4. The second one is this 3, and then minus 15. So can you tell me what the x plus 4? What does the plus 4 do? Does it move it left or right?
Left 4.
Left 4. Okay. We'll talk about from where, but let's keep going with this. So what is the 3? Is it a horizontal or vertical stretch? And keep in mind, it's kind of outside the parentheses now. Are you with me, Julia?
Yes.
Okay, so the 3 is a vertical stretch of 3.
Mhm.
And then what about this minus 15?
Down 15.
Perfect. Okay, so the parent function, which is probably the first thing I would ask you, I'd say, what is the parent function? The parent function here is square root of x. The square root of x looks like this. It starts at 0, 0, and it goes up and to the right. So again, you have your choice. You can like know the parent function of this, which I would want you to know as a student. I would say this is really important, worth knowing. And then here are your y values. So the choice is you can either well, see, this one's made more challenging because it shifts both x and y. The left 4 changes this, but then these change the y's. Okay, so we'll do that here. We'll see if that approach works. So left 4 means every single x value is going left 4 or subtracted 4. So minus 4, minus 3, 0, 5, and 12. Okay, but then vertical stretch of 3, that affects the y value. Anything on the outside affects the y's, the inside affects the x's. So a stretch of 3 means you first multiply by 3 and then you subtract 15. So 0 times 3 is 0, subtract 15 is minus 15. Same thing with the 1. You're going to multiply by 3 and then subtract 15. So times 3 is 3, subtract 15 is minus 12. Same thing here, multiply by 3, that's 6, minus 15 is minus 9. multiply by 3 minus 15, multiply by 3 minus 15. All right, so then you got to graph these points. And you also need to know that it does start there and it goes to the right, like, so that it does not extend past this. So this, I mean, this isn't great. These are kind of weird points that they're doing. So the thing is it does cross, and that's what I think the problem with this. I don't know why they chose this problem, but it does eventually cross. Way out here, it crosses.
Mhm.
And your graph needs to reflect that. Like, you wouldn't want to show that it did not cross, because it does. But that's the nature of this. You don't have, they didn't, if they just changed this to like -5, then it would give you something nice, but they didn't. But you need to know that as a student that does cross, okay? Because you, for your end behavior here, like as x goes to infinity, you need to know that like this goes, while it looks like it's flattening out, it literally, it does go up forever. So y goes to infinity. And then as x goes to, well, it's not negative infinity because it stops here. So what is that stopping point? It's the x value. It's the x value of -4. So as x goes to -4, whatever the stopping value is, which in this one, it would be 0 in the parent function. But since it moved left 4, that's why it's -4. And this time, well, what is the y value approach? It's the y value here, which is this minus 15.
Okay.
All right, so I think we have enough time to cover this even odd concept before moving on to, or that, I mean, that'll probably be it for today's lesson. If you're okay with that, we can cover even odd in the last few minutes, or something else, up to you. So a function is even if the following is true: f of -x equals f of x. And you don't care about that, but what you always do first is you evaluate f of -x. You actually go back to the original function and you put -x in for x. Okay, and this is where you got to be really strong on, like, what is -x to a even power, like 2? Well, it becomes positive. But if it's -x to an odd power,
Mhm.
it stays negative. So this becomes -x cubed -5. Okay. Now, the very first question you ask yourself is you say, is this right here? Is this f of x? Is it the same as f of x? It has to be exactly the same. Is this the same of f of x up here? Exactly the same. No changes.
Wait, which part is?
This right here, is this right here, is this f of x? Is it exactly the same as what you have there?
No.
No. Okay. If it were yes, this is what's important. If it were yes, then it is even. Okay. All right. So now the next thing you do is you factor out a -1. So you factor out a -1 out of this. So all I'm doing is taking a negative out of this -x cubed and this -5. So now you look at this part right here inside parentheses and you say, is this f of x? And I'll go back up to it. F of x is x cubed -5. Is this f of x, the part inside this?
No.
No. If it were yes, it would be odd. Okay, so maybe we need to say yes means even, yes means odd. When you get no, that means it's neither.
Okay.
Okay, so let's look at one that is odd. So you can see this. You can see how this plays out. So this one is odd. I'm telling you that from the start, but we're going to still try it. So we're going to go g of -x. So -x cubed -5 times -x. Again, probably a really good strategy to put it in parentheses each time. So this becomes -x cubed. This minus and this minus go together. That's 5x. So you first look at this and
Mhm.
you ask yourself, is this exactly the same as the original? Exactly, exactly, exactly. It has to be exactly the same. The answer is no. So it's not even. Then you
Mhm.
factor out a -1, which means you're just changing the sign of each of these. So now you look at this part and you say, is this the same as the original? Yes. Not the negative, the part inside parentheses. Yes. That means it is odd. Okay, so really quick here, let's say f of x equals minus x to the fourth minus x squared, or let's do plus x squared. And let's try negative x inside here. This is negative x to the fourth plus negative x squared. This becomes negative x to the fourth. This minus becomes positive because that's even, but that negative stays. Plus, same thing here, x squared. And you ask yourself, is this the same as the original? Yes. And so that's even. So the progression is check if it's even, factor out a -1, check if it's odd. If it's neither of those work, then it's a neither case.
Okay.
How do you feel going into your diagnostic? You think you said it might be tomorrow.
Yeah, I feel much better. now.
Okay. Okay. We've done a lot of prep work. Try to go in there with a,
Yes.
try to not have the anxiety, trust yourself.
Mhm.
But yeah, thank you for letting me help you. I'll send you out the notes here shortly, and I'll see you next time.
Okay, thank you so much.
You're welcome. Have a great night. Bye now.